I hope everybody is fine. And in this video, we are going to proceed from our quasi-classical case that we discussed in the previous video. Uh, and It was where we developed the wave function for the allowed region and for the forbidden region, and we have turning points. If I likely remind a situation like this, where we have potential that's varying in this fashion, and assuming this to be x1 and this to be x2, these 2 points are called turning points, and between x1 and x2, E is less than V of x, and beyond x1 and x2 we have E. Oh, here we have E greater than V of x, and here we have E less than V of x. So between x1 and x2, what we have is we have allowed region, and beyond x1 and x2 we have forbidden region. So here we have allowed region, and here we have forbidden region in classical domain. So this is classically allowed region, and this region and this region is classically forbidden region if I choose this as reference of the total energy. So here we have E greater than that of V of x, and this region is classically allowed, and then we have classically forbidden region, and the point x1 and x2, where we have E equal to V of x. This is what is called as turning point. I mean, classically the particle will come to rest at point x1 or at the point x2. So the y-axis is the representative of V of x. So if I quote down this potential with no rigid walls into three regions, and let me call this as region 1, region 2, and region 3. And what is so important is that if I talk about x less than x1, if I talk about x greater than x2, these are classically forbidden regions, and between x1 and x2 we have classically allowed region, and then talking about x1 and x2, these are classical turning points. Now, what is important here is that this is suitable and simple example to illustrate the various aspects of this quasi-classical method, and notably how to determine the particle's wave function at these turning points. And what is important here is that we would like to see this method, this quasi-classical approach. It automatically leads to Bohr-Sommerfeld quantization. It leads to Bohr-Sommerfeld quantization rule. Quantization rule. All right, and this quantization rule, from which we have the bound state energies, ought to be extracted here. And talking about again this quasi-classical case, I mean this method applies everywhere in the three regions 1, 2, and 3, except the turning points at x1 and x2. At these points, E is equal to V of x, and here it is E is equal to V of x2. Okay. And the quasi-classical approximation to the wave function in this region 1 and region 3, we can execute the solutions for these two regions, and the approximation in the region 2 can be extracted from the wave function that we have developed for E greater than V of x, and for classically forbidden region we can have the approximations for E less than that of V of x. Now what happens here is that the wave function at these turning points, after these turning points, the wave functions, they must decay. They must decay exponentially in the region 1 and region 3 as x tends to infinity. I mean, we can have a limit from as x tends from minus infinity to plus infinity. So there is exponential decay of wave function in region 1 and region 2. But if we talk about in region 1 and region 3, but if we talk about the region 2, this region 2 is purely oscillatory in nature. So this region is the reflection of the oscillatory motion of the particle. So if we stand out to write down the wave function, so psi of x. Now if I choose a region x less than x1, then this psi of x, if I take it as a1 by under root of, which is already developed in the previous video, magnitude of p of x, exp minus 1 by ih cross x to x1 p of x d of x. So for the region x less than x1, the wave function is going to decrease exponentially beyond these turning points x1 and x2, and we can so it would be right to talk about here. So I'm less than x1, so this is my region 1, so I'll call it psi 1 of x, and then we can write down psi 2 of x as say a2 by under root of p of x, and then exp of I by h bar x to p of x d of x, then close it, plus a2 dash by under root of p of x exp times minus I by h bar integral of x p of x d of x. So this will be my wave function in the region 2. So the range of this region is from x1 less than x less than x2. So what we have done, we have written down the wave function for region 1, and this is perfectly exponentially decreasing. Then we have written down the wave function for region 2, where certainly when we have those mathematical simplifications for this, will lead oscillatory function at the end of this psi 2 of x, and then writing the wave function for the third region. So I'll call that, say, psi of 3. So psi of 3 will be for x greater than x2, and in this case I'll take psi 3, say c3 by under root of p of x, the magnitude of it, then exp times minus 1 by h bar integral x2 to x, then p of x magnitude d of x. That's it. So what we have here in all the three equations, we have introduced some constants, and these constants that we have, say a1, a2 dash, we have some constants a1, a2, and a2 dash, and c3. These constants have to be determined, have to be calculated, and And what is important for them is that we must be able to connect the solution of. So what is important here is we have to connect the solutions. I mean, psi 1 of x and psi 2 of x and psi 3 of x. And while we have been pausing from region 1 to region 2 to region 3. So there is certainly the need of connection that we are supposed to have from one region into another region through these crazy turning points. So these crazy turning points that we have, x1 and x2, where quasi-classical approximation ceases to be valid, because quasi-classical approximation doesn't seem to be valid at these turning points. So that's why we need to connect these wave functions. I mean, we need to connect psi 3 with psi 2 as we go from 3 to 2. And then we need to connect psi 1 to psi 2 as we go from 1 to 2. And since this quasi-classical approximation, it breaks down at x1 and x2, we certainly need to look for some exact solutions of the Schrodinger's equation in vicinity of x1 and in vicinity of x2. So let us first build a connection relation from psi 3 to psi 2. So connection. So let's try to obtain the connection relation between psi 3 and psi 2. All right. So in doing so, what is important is we already have written down psi 2 of x. Okay. So in this case, okay, better is to write it down again in order to be consistent with the video. What is it? We have psi 2 of x, and what is that? Psi 2 of x is a2 by under root of p of x. Then we have exp I by h bar integral x p of x d of x. This is certainly the magnitude of momentum, and then plus a2 dash by under root of p of x, and then exp minus I by h bar integral p of x d of x. All right, so this is our psi 2 of x, and we can see that we have a situation like exponential functions, and this equation can boil down to the sine function. So on solving this equation, we can write down psi 2 of x as we have a2. We will introduce another constant, say a2. Let me introduce a3 here. So a3 by under root of p of x, sine of 1 by h bar x2 p of x and d of x plus alpha. Now, what is this alpha? This alpha is a phase, and this alpha has to be calculated. This alpha has to be determined. Since quasi-classical approximation breaks down near the turning point x2, so what we have the turning point x2, and this is x1. So what is happening to this quasi-classical case at the turning point x2? It breaks down there. So what is important here is that we have to find a scheme, we have to find a way out for determining the wave function in vicinity of this x2. And for that, we can look for some exact solution of Schrodinger's equation near this x2. And as has been talked about, now if we think of x minus x2, if we take its magnitude, if we assume this magnitude is extremely small, if we choose it very small within the region of x minus x2, what we can do here is we can approximately represent the potential by the straight line. If this increment between x and x2 is extremely small, and we can represent this by a straight line, and the slope of this straight line is equal to that of the potential at the classical turning point. That will give us the measure of the potential at the classical turning point, which we have been defining here as x equal to x2. So in that case, so we are here. This is our classically allowed region, which is oscillatory in terms of sign, and we can think of expanding this v of x nearly as v of x2. Then we can expand this as x minus x2 dv of x by dx at x equals x2. So if we choose that this v of x2 is equal to e, then this v of x that we have will be e plus x minus x2 times some f, because we better know that this f is dv of x by dx at x equal to x2. So we can approximate this potential. This potential can be approximated to e plus x minus x2 times dv by dx, and we better understand that this dv by dx is nothing but the force. And the Schrodinger equation for the potential that we have been defining here, we can write down Schrodinger's equation for this as d2 psi of x by dx2. So there will be cancellation of e, and there will be some cancellations involved here, and we will come up with minus 2mf by h cross square x minus x2 of psi of x equals 0. And we would like to use some changing variable here, say zeta, and take this zeta equal to 2mf by h cross square whole raised power 1 by 3 x minus x2. Now if you do that, what will happen, we will transform this equation. This equation will be transformed into something like this: 2mf by h cross square whole to the power of 2 by 3 times d2 psi of zeta by d psi d zeta 2 minus zeta psi of zeta. This is going to be equal to 0. So what's done is this this chosen variable is introduced in the Schrodinger's equation, and it has been converted into this equation. And this term cannot be equal to 0. So what is equal to 0? This is d2 psi of zeta by d zeta 2 minus zeta psi of zeta is equal to 0. Now, this is a well-known equation in mathematics. This is a known differential equation whose solutions are generally expressed in terms of the Airy functions. Airy functions. So we'll not go into the details of those functions. What would I suggest here is that on evaluating, on solving this differential equation and introducing some constants, what we finally achieve here is that we achieve that the alpha that we have introduced in psi 2 of x, the alpha that we have introduced here, the phase alpha, this alpha comes out to be equal to pi by 4. That can be an exercise for you, and you can do it. Certainly, you can do it. Okay, so so what we can do now is we can write down the connection equation here. So what we will have a connection formula for this quasi-classical case, and what we have here is we have psi, I'll call it psi 2 of x now. It is between 2 and 3, and this gives me, what was the, it was a3, it was a3 by under root of p of x magnitude. Then we have sine of 1 by h bar x to x2, and then p of x d of x, then plus pi by 4. So this is our connection relation between 2 and 3. So I should call it 2 to 3. This is the connection relation between that. Now, the same quasi-classical equation has to be developed using the same mathematical formulation between psi 1 and psi 2. So we want to have a connection, relation between psi 1 and psi of 2, psi 2 of x. So if I write down psi 2 here, okay, so what is my psi 2? And I can write down the same kind of thing will be there with different constants, because the problem is symmetrical in nature, and we will have psi 2 to 3. What were the constants that I have used for them? Let me come up with new constants. So let me introduce a constant c2 dash by under root of p of x exp. Then we have I by h bar integral x1 to x, then p of x d of x, and then we will have plus c2, this is c2 dash, this let us take this as c2 double dash by under root of p of x. There may be something wrong with the constants. The constants don't change physics, basically. What is important here is to take to have some consistency. So this is exp, then we will have minus I by h cross x to x1 p of x d of x, and certainly we can boil down this this equation can be boiled down to psi 2. This is between 1 and 2, so this can be psi 2 of x equals d by under root of p of x, then sine of 1 by h bar integral x1 to x p of x and d of x plus here let us introduce the phase as beta. All right, and we can go back to a situation where we have here x equal to x1, and certainly the quasi-classical case breaks down there. If we go back to that symmetrical problem that we have been discussing here, so this is x1, this is x2. Now here we have the same kind of situation as we have been talking about, and this problem can be dealt in the similar fashion as I talked about the problem that was dealt at x2, and doing the same mathematical analysis we will obtain this beta that we have introduced, again equal to pi by 4. So we have psi 2 of x. Now this is from this is psi 1 2. Let me call it psi 1 2 because it's a connection between 1 and 2, and this is my my psi 2, 3, the connection between 2 and 3. So this psi 1, 2 is to be written as this is equal to d by under root of p of x and sine of 1 by h bar integral x1 to x. Then we have p of x and then d of x and then plus pi by 4. So we have two equations which are mathematically connecting the two regions, the classically allowed region and the classically forbidden region. And if I write down these two equations now, so we have what we have is we have psi 2, 3 of x, and that is a3 by under root of p of x, and then sine of 1 by h bar, then integral x to x2, then p of x, then d of x plus pi by 4. And then we have psi 1 of 2, psi 1, 2 of x, and that is d by under root of p of x, then sine of 1 by h bar integral x1 to x. Then we have p of x and d of x plus pi by 4. That's the case. Now, since we have these two solutions, and these two solutions certainly represent the same wave function in the same region, so they must be equal. These two wave functions must be equal. So I can say that this psi 2, 3 of x is equal to psi 1, 2 of x. So this connection relation psi 2, 3 of x must be equal to psi 1, 2 of x. Or we can say that because our problem is symmetrical at x1 and x2. So symmetry also dictates me that this psi 2, 3 must be equal to psi 1, 2. So that means there must be the equality between these two equations. So this whole thing is equal to this whole thing. So let me write down that. So what will be that? That will be, so if I use d by under root of p of x and sine of 1 by h bar integral x1 to x p of x d of x plus pi by 4 must be equal to a2, no, that's a3 by under root of p of x, then sine of 1 by h bar integral x to x2 p of x d of x plus pi by 4. Now we can see that this equation, this is an equation of the form like d sine say d sine theta equals a3 sine, I'll call this theta 1, and a sine theta 2. Now its solution, the solution must satisfy the given condition. The solution of this equation must satisfy that this theta 1 plus theta 2 is equal to n plus 1 times pi. This is the first condition, and the second condition is that this what we have here, a3 and d, they must be related like d equal to minus 1 whole raised power n and a3. Now taking this equation into consideration, now what's that? Theta 1 plus theta 2, that means this whole thing plus this, this whole thing must be equal to n plus 1 pi. So what we can do is we can write 1 by h bar integral x1 to x p of x d of x plus pi by 4. Now this thing plus 1 by h bar and integral where from is that integral x to x2 p of x d of x plus pi by 4 must be equal to n plus 1 times pi. Now what we can do is we can proceed from here, and what we can see here is that we can stretch down this, we can compress these two integrals into x1 to x2 1 by h bar p of x and d of x. So it would have been rather good if we had used prime for p of x. But we anyway we can proceed like this. P of x d of x is equal to n plus 1 by 2. Oh, this must be equal to n pi plus pi, and this pi by 4 plus pi by 4 will give us 2 pi by 4. So 2 pi by 4 means pi by 2 will go on to the other side of the equation, so we'll get here minus pi by 2. And we can see this h bar will be multiplied, so we'll have x1 to x2 p of x d of x is, this is n pi, pi minus pi by 2 will give us minus pi by 2 times h bar. So this is n, so this is plus, okay, so n plus 1 by 2 times h bar is integral from x1 to x2 p of x d of x. All right, that should be the case. And since this integral that we have, this integral is between the turning points. If I plot down my problem, we have a problem like this, and we have a symmetrical situation. This is x1 and this is x2. Now the integral that we have here is between x1 and x2. That means it's between the turning points. And this integral x1, x2, p of x, d of x is equal to the half of the closed integral for p of x, d of x. And what then is going to happen is this integral x1 to x2 p of x d of x, this integral can be written as 2 times p of x d of x. Okay, so what we are going to get here is so we will have integral closed p of x d of x is 2 times what we have here, 2 times n plus 1 by 2 h bar. Okay, that's the case, and I think I forgot pi. So this is 2 times n plus 1 by 2 times, what is h bar? This is reduced Planck's constant. This is h by 2 pi. So here we have pi, this pi, and pi 2 and 2 will cancel. And what we will have is n plus 1 by 2 h integral p of x d of x. Now, in quasi-classical case, this n is very, very greater than 1 by 2. So we can boil down this to p of x, d of x is equal to nh. And this relation determines the quantized quasi-classical energy levels. And En, or I mean the energy of the bound states of the semi-classical system. Now it is exactly similar to the Bohr-Sommerfeld quantization rule, and which in turn is known to represent an improved version of Wilson-Sommerfeld's rule. So this is our Bohr-Sommerfeld quantization rule that we have achieved using quasi-classical case, using WKB approximation.